UT. Welcome to the IAU Commission as a local universe seminar. And today we will hear a presentation by Juri Poutanen from the University of Turku in Finland. And he will present his work on X-ray binaries using polarimetry. So welcome, Juri, and please share your presentation and present your work.
Thank you. Okay, so I hope you see my presentation now.
Yes.
So this is the topic that we have been busy for the last at least couple of years, very busy. And actually, we started to prepare the X-ray polarimetry many years ago, polarimetric missions, but finally, a couple of years ago, we managed to get the satellites flying so that we can actually now study the compact objects, in particular X-ray binaries using in the polarized light. So today I will cover only X-ray binaries, and even those quite briefly. So basically, the problem with X-ray binaries is that we cannot resolve the emission regions. The emission region size are nano-arc seconds, and it's 1,000 times smaller than the size than the, for example, event horizon size in the black holes on M87 or Sagittarius A star. And so here you have the image from the Event Horizon Telescope of the gas surrounding the supermassive black hole in M87. Unfortunately, we are not lucky, so we cannot do imaging. The sources are too small. We have to learn about the source geometry some other way, and polarimetry is the way to do that. So polarimetry is known, provided it was very important in radio, infrared, optical band, and people have been using it for already many years. And in X-rays, of course, we have a number of processes that produce polarized light, like, for example, any non-thermal process like synchrotron emission. If you have ordered magnetic field, produces high polarization. And if you have scattering, then any sphericity will be producing polarization. And looking at this, we will be able to understand the geometry of the emitting sources. Unfortunately, polarimetry in X-rays wasn't possible basically until the end of 2021. And the only reasonable observation of a source, one source, Crab Nebula, was done in the middle of 70s. And this is integrated emission, and in X-ray band, the polarization was measured at 19%. So this is basically demonstrates that in Crab Nebula we have synchrotron emission. And of course, if you make the images of the Crab Nebula in various bands from radio to the X-rays, now you see the spectacular images. In all the bands, you can also make the similar image of the magnetic field, basically, because the polarization is perpendicular to the magnetic field direction from radio to the optical, but not in the X-rays until just the last, last 2 years. So X-rays, as I said, they tell you about compact object, because most of the compact object, they are bright X-ray sources, and they tell you about where the particles are, like electrons, let's say, accelerated. So they tell you more about compact regions where the actions is actually going on. The story about X-ray polarimetry actually started somewhere in the middle of the 70s, 1970s. And there was a mission which is called OSO-8, and this is the mission that actually made basically one observation. Unfortunately, it wasn't sensitive enough. Later, there were proposals to put X-ray polarimeters on board of various missions, Einstein, Spectrum X-Gamma, GEMS. It was accepted, NASA mission, but it was cancelled. Then there were plans to put it on the big missions like Zeus, IXPE, which, as you know, never realized. And so people tried to do it without much success, because polarimetry is actually photon hungry. you need, if we want to detect a photon with Chandra telescope, you need maybe 3 of them. If you want to detect the source, you need 3 photons. But if you want to measure polarization with accuracy 1%, then you need 1,000,000 photons. So that's the difference that we are down to. And so in December 2021, IXPE, Imaging X-ray Polarimetry Explorer, was launched. This is the NASA mission with collaboration with the Italian Space Agency. It has 3 telescopes on the March, which is like 10 meters apart, and then there are 3 detectors, basically identical. And it can measure X-ray polarization of the X-ray light using a photoelectric effect. So before, all the detectors were based on scattering, Thomson scattering or Bragg spectrometry, but they were not very sensitive. But the electric effect turns out to be sort of a good physical effect that you can use. And the physics behind it, that if you have photon with the polarization on the plane of the image here, and it ionizes the gas in your detector, you have photoelectron flies out, and the direction of the photoelectron, it actually correlates with the polarization. The cross-section, differential cross-section, is proportional to cosine square of this azimuthal angle. So basically measuring the angular distribution, azimuthal distribution of the photons, of the photoelectrons, you can get the you can measure polarization. And how you do it, there are 2-dimensional detectors. You have the photoelectron leaves the trace here in the detector. You have anode, a cathode, and so you basically read out where the photoelectron was flying. And then you, from the image of this, you can sort of get where what is the original direction of the photoelectron. And then you plot these directions when you detect many photons as a function of azimuthal angle. And from the amplitude of these variations as a function of azimuthal angle, you can measure polarization. An important quantity is so-called modulation factor. Basically, how big is this amplitude for the 100% polarized source? And the bigger it is, the easier it is to measure polarization. Fortunately, these detectors give you like between 30 and 60% of modulation factor, so which is actually good enough to measure polarization even from weakly polarized sources. Okay, so basically, IXPE now has been operating for slightly more than 2 years, and this is the list of different types of sources that IXPE has observed. As you see, there is a long list. We have 8 working groups, and the 9th is other, which means the gamma ray burst. The mission wasn't designed to observe gamma ray burst. And so you see there is accreting X-ray pulsars, non-magnetic neutron stars. These are those objects that I will try to mention today. You have magnetars, pulsar nebula, supernova remnants, stellar mass black holes, supermassive black holes in Seyfert galaxies and blazars. Okay, so there are plenty of papers have been published, more than 50 by now. Some of them are in Science, I think 2, 3 in Nature, few in Nature Astronomy. So this is the outcome of, and so therefore, as you see, it's impossible to cover everything in 25 minutes talk. So we will have to pick up all those things that I promised about X-ray binaries. So I will try, now I will start from the X-ray binaries, which is contained in black holes. So this is the artist impression. You have a black hole here accreting the gas from the companion star. There is accretion disk, there is maybe a jet injected. And in these sources, and the most famous was Cygnus X1, it was observed, there was the first source, the first stellar mass black hole that was observed by IXPE in the May and June 2022. The main questions were about the emission geometry. The source has this kind of 2 states, soft and hard. This is new spectrum. You have in the hard state, you have most of the energy comes at 100 keV. The spectrum is formed by multiple Compton scattering. So basically, some soft photons are upscattered by hot electrons, and they gain energy producing this powerful looking like spectrum. But where this is happening, what is the emission geometry? This is a matter of debates. There are many proposals of some corona above the accretion disk, called accretion disk, some patchy corona with flares, hot flow. You can have even some lamppost models were introduced to try to measure spin of the black holes or the base of the jet. And so there were many speculations in the literature. Fortunately, polarization is sensitive to the geometry of this emission region, to what we will call it corona. It actually is sensitive to dynamics and the source of seed photons if you are capable of measuring energy dependence of polarization. So as I said, it was Cygnus X1 was observed a couple of times in 2022 in the hot state. It was observed later in the soft state too. I will not mention that today at all. It's another topic. And this is the most interesting result. It was that polarization was detected with very high significance. That was about 4% polarized in source and X-ray band. Polarization angle minus 21 degree, which means that this preferential direction of the electric field is into the west from the north. And amazingly, this direction perfectly coincided with the direction of the radio jet. So in the right, you have the radio image. You have the elongation along the same direction, and this orange, the yellow line, is the direction of the polarization that we measured. So this is very interesting result that polarization turns out to be parallel to the jet. So how do you explain that? If you have some X-ray emitting region, which is, let's assume it's a slab, plane parallel, then if photons are scattered many times and flying back and forth in this slab, and then when they scatter, they fly towards us, then the electric vector will be perpendicular to this slab, which means if the jet is parallel to the normal to the slab, polarization will be parallel to the jet. And so immediately when you measure this high polarization, what you learned, we learned that the emission region has to be very elongated. It cannot be spherical corona. It can be cylindrical, elongated along the jet. It has to be elongated perpendicular to the jet. So basically, immediately, these observations rule out all the lampposts based on the jet models. So one can forget about those. They cannot produce X-ray polarization. So we now know that the X-ray emitting region is probably much closer to this figure E here, which is some plane parallel, more or less flattish emitting region, because 4% polarization is actually very large. Yeah. So we didn't expect that. All the models predicted 1-2% maybe, so 4% was quite surprising. Second object that I mentioned, that's another Cygnus source, Cygnus X3. The source was also known for, as from the name you can guess, it was known for many decades. Quite far away. This is from more than 7 kiloparsec from us. It's a compact black hole, probably a black hole with a companion, which is the Wolf-Rayet star. And so we have orbital variations here shown. There is some sort of absorption by the wind from the Wolf-Rayet star. Okay, and there is a jet that we know that basically the direction of the jet is north-south, so position angle 0, basically. And the problem with this source that actually it's very peculiar. It's very high absorption. And if you look at this near spectrum of the source, so this is the same source, and there are 3 different models how to explain this. Either you have a lot of soft photons here, or they're strongly absorbed, or there is a hot spectrum here in the middle that is less absorbed. And so people make various models that, and it was not clear what is the correct one. It looked hot spectrum, looked like Cygnus X1, but because of the strong absorption, it is not really the same. Okay, so IXPE observed the source without much of the expectation, but the result was a big surprise. Polarization was detected with a huge significance. Polarization degree in one of the observations was more than 20%. Polarization angle 90 degrees, so which means perpendicular to the jet, not parallel like in Cygnus N1, but in perpendicular. We triggered another observation where we observed the source in slightly different state. It was 10% polarization, exactly the same polarization angle. First thing to notice that polarization degree is basically independent of the energy. There is a dip here in the blue at around iron line, which is fluorescent iron line, which is not polarized. Okay, But otherwise, in the whole of the continuum is very well consistent being constant polarization degree. It's very large and constant. And judging from the spectrum here, we immediately realize that if it's constant, but it's just because of the line, the absorption, the polarization drops, it means that all these photons are produced in one single scattering from somewhere. Okay, so we don't see really the central source, which is probably not polarized at all, but we see some reflection. And this is the model that we came up with. So this is sort of the wind from the accretion disk. And it makes like a funnel, empty funnel. The central source, which is probably somewhere close to the black hole, produces photons which are reflected from the inner side of this funnel in the surface, and then they go towards the observer. And from the polarization degree, you can actually measure the geometry of this funnel. We can say that we made simulations, and then we basically concluded that such a high polarization degree, which is more than 20%, for that you need the and inclination, we know about 30 degrees of this source. We need the opening angle of this funnel just about 10 or 15 degrees. Okay, which means that actually you cannot look directly towards the black hole, but you look at this reflected signal. But there is a strong wind from the accretion disk that blocks the central source. You see only reflection signal. We made the simulations and trying to understand what's the luminosity of the central source, the intrinsic luminosity, and we got about 10 to 39 ergs per second. And because we see factor of 10 lower luminosity because it's only reflected signal, the observer along the axis here would see actually much higher luminosity because the photons will be beamed towards the observer. It could be easily 10 to 40 ergs per second. And this would qualify the source to be a ultra luminous X-ray source. We are not lucky to see that bright luminosity just because our inclination is larger. But basically, the IXPE results prove that Cygnus X3 is a hidden ULX, which no one ever even suggested or thought about this. So this is absolutely new, interesting result. Let me switch to some other object now, to the accreting neutron stars, and the brightest of them are X-ray. So the bright types of sources are X-ray pulsars. These are neutron stars with the strongly magnetized neutron stars. Sorry. That accrete gas also from the companion. Here we have the artist impression. How it's happening. You have accretion disk, and there is a accretion funnel, accretion stream that hits the neutron star surface. Depending on the accretion rate, this emission can be at high accretion rate. You can have the so-called accretion column emitting, and at low accretion rate, the matter just hits the neutron star surface, and most of the emission is produced at the neutron star surface. Okay, and so the aim when we try to observe it, we try to get the geometry of the emission region and try to maybe test so-called free precession model for Hercules X1. Hercules X1 was the first X-ray pulsars where the cyclotron absorption line was discovered in the end of 70s, and it proved that these are strongly magnetized neutron stars with a magnetic field in excess of 10 to the power 12 Gauss. We expected that these sources are strongly polarized, because in the magnetic field, the opacity from the two polarization modes, O and X mode, are very different. So if the photons, polarization of the photon electric vector oscillates in the plane made of the direction of propagation and the magnetic field, which is called O mode, the opacity is not much different from the Thomson, below the resonance, which is at very high energies. But in the X mode, it's now the colors are sort of different. The X mode electric field oscillates in perpendicular direction, so it's actually difficult to drag the electron across the magnetic field. The opacity drops. So therefore, because the two modes have very different opacity, we expected these sources will be strongly polarized. This was known from the papers already by Misaraj in 1988. It was a model. And if the magnetic dipole is misaligned from the rotational axis, which is, of course, you expect because it is a pulsar, so it rotates, and you see pulsations. And in phase with this pulsations, you should see change in the polarization angle. So basically, position angle of the dipole projected on the sky should tell you what is the polarization angle, or actually measure the polarization angle as a function of pulsar phase. You will be able just to measure the position angle of the dipole. So you can get constraints of the geometry. And this is so-called simple rotating vector model, which is just a stick rotating around the rotation axis, okay? What's also interesting that the photons propagating the magnetosphere in vacuum, basically, the polarization will be adjusted to the magnetic field geometry up to 20-30 stellar radius because of the effect which is called vacuum barrier fringes. And at those 20-30 stellar radius, the magnetic field is basically dipole. And all other multipoles drop much faster with the radius, with distance. Therefore, you would expect that actually when you observe the X-ray photons, you will actually be able to measure the geometry of the magnetic dipole. Okay, and what's actually we can see, I will just give you one example. We observed more than 10 sources by now, but Hercules X1 was, the most interesting. We wanted to see how geometry of the neutron star changes of different phases. This is superorbital phase, so superorbital period, the 35 days. Okay, so this is the phase of the superorbital period, which is related to some precession of the accretion disk around the neutron star, and people think that also is related to the precession of the neutron star itself. Okay, we observed the source in the so-called main on, which is when the source is bright, and then we observed later the source in the short on, which is when the source is factor of fuel weaker. Okay, and here there are main results that when you look at the behavior, this is the lower panels are the most representative. The polarization angle as a function of phase is very different in the three observations. So you can basically see that from even in the main on, separated by a year, are quite different. But the short on, it was the position of the polarization angle behaved a completely different way. And we can feed the data with the rotating vector model, and we can get geometrical parameters. And what we learned that actually the inclination of the pulsar is changing from the phase to phase. So basically, and the position angle of the axis, rotation axis, is also changing. So basically, this is the strong evidence that there is a precession of the system. And now there is a paper in press and Nature Astronomy that actually shows what is tells about the physics, what is the moment of inertia of the crust of the neutron star, which is dragged here by some external forces, but also because of the neutron star asymmetry, asphericity. You have this precession of the neutron star. So what's basically happening, that of course angular momentum is, if you don't have external forces, angular momentum is conserved, but because the star is not spherical, and the magnetic field is, somewhere, the way you see the neutron star will be changing at different phases of this precession. And you can actually try to explain how it precesses, what's the velocity. I mean, it's 35-day period, you can explain with this and so on. So basically, it's a good evidence for the previously, long time ago, proposed precession model for the neutron star in Hercules X1. The final topic that I will discuss today, these are non-magnetic accreting neutron stars. These are also neutron stars, but which do not show pulsations. So presumably the magnetic fields are here much slower, below 10 to the power 8 Gauss. And we will be talking about these bright sources, which are in this so-called soft states. You have an accretion disk and you have some boundary or Stellarian layer where accretion disk interacts with the neutron star surface. So you can see these two components, the accretion disk and the boundary layer in the spectra. So the accretion disk is softer because it has larger size. And then the high energies, the radiation from the boundary or spreading layer dominates. One of the sources we observed was Circinus X1. This is the youngest X-ray binary of the sky. This is about less than 5,000 years old. It's quite a eccentric system with orbital periods about 17 days. We observed it twice. And the most spectacular result was that polarization angle that we see in different occasions is different. We try to divide the data in different times, the segments, or different hardness ratio, and we see that from time to time polarization angle just is very different, and this was actually different by 70 degrees. But we have just a couple of snapshots, so not very long observation, so it was very difficult to understand what's happening. So Vadim, who is actually here listening, produced this nice picture. So we try to explain this by misalignment of the neutron star from the rotational axis from the orbital axis. So you can imagine that we have an accretion disk, which is rotating this way, but the neutron star is lying on the side a little bit. So you can have gas which is accreted to the neutron star, dragged by the neutron star rotation, and then therefore the symmetry axis for this emission region at the neutron star will be related to the rotational axis of the neutron star. But if you have higher accretion rate here, then you can have emission from the boundary layer, which will be the symmetry axis will be related to the accretion disk axis. We don't have any hydrodynamical model for this, but we just speculated that the only thing that comes to our mind is that you need to have strong misalignment just to get these different angles observed different times. Otherwise, we just have no clue what's happening. So there's a really mystery that we haven't solved. We have a suggestion, but this is not really the last answer. Later on, we observed another source. Actually, we observed many, but this is the most spectacular also, JX13+1. For about a few days. This is the light curve on the top. We divide it into 5 different bins, and in the Stokes parameter plane, Q and U, we see that it varies a lot. And if you just plot polarization angle at different bins here and as a function of time, you see the polarization angle varies, changes basically in a linear fashion with time by also 70 degrees. And it's not two different different polarization angles that we have detected in Cirrus X1, but this is a slow rotation, slow but quite fast, because this is over time scale of a couple of days. It rotates by 70 degrees, and it's not a pulsar, right? So this is non-magnetic neutron star. We don't see any pulsations, and again, the only model that comes to our mind that you need some misalignment just to have this. Maybe there is a precession of the neutron star that forces this axis to rotate by 70 degrees. So you can imagine that the neutron star here, it goes from the left inclined to the left to the right. And if it has inclination 30 degrees relative to the accretion disk axis, and then the polarization angle might change by 70 degrees. So this is like the speculation that we can only put in. And actually, we have no clue what's happening. But this is really amazing. Very puzzling result that is now we have to deal with, and maybe in the future we will be able to understand. And so basically, I would like to conclude here with saying that Imaging X-ray Polarimetry Explorer has opened a new window to the universe, which is X-ray polarization, X-ray polarimetry. We can now study a number of sources. About 60 papers or 50 papers have been published. Many have been submitted now. And using the X-ray polarization as a function of pulsar phase or the function of energy, it depends on the source, function of time. It's actually, you can understand a lot of things, and it's already clearly revolutionizing our understanding of X-ray binaries. Some of the things that we really don't understand still, so it's maybe revolution still on the way. IXPE allows now to measure geometry of the emission region in the accreting black holes. We now understand that there is a hot flow which is perpendicular to the jet. We rejected compact X-ray sources like lamppost corona. So basically, the conclusion is that if there are some black hole spin measurements based on this lamppost model, maybe they're not really physical. We can now measure pulsar geometry very accurately. I showed you the example of Hercules X1, where the precession seems to be confirmed. We have now measured pulsar geometry in another 10 sources. And we find evidence for misalignment in non-magnetic neutron stars, which is also a mystery. So in the future, this is the map of the X-ray sky of the galactic coordinates. You know, what we want to have, of course, with the IXPE and maybe in the future with the X-ray Imaging, IXTP, the Chinese mission, which will have also a couple of times bigger telescopes, effective area doing X-ray polarimetry. But already now, we managed to get to cover most of the sources which were proposed like a few years ago to be observed by IXPE. So we have observed pulsars, we have observed radio galaxies, and I will say we have observed supernova remnants, I think 4 of them, X-ray binaries containing neutron stars and black holes. Yeah. And then the wind accreting X-ray binaries like Vela X-ray X1, the pulsar. We have magnetars, few of them observed. Galaxy clusters we haven't observed. We don't expect high polarization there. Blazars, a number of them. AGNs we have observed. GC 4151, IC 4320AA, and so on. X-ray pulsars I mentioned. A pulsar with nebula, Crab nebula, Vela pulsar with nebula, and so on. So this is hopefully they already have observed more than 50 sources, and IXPE now has at least a couple of years in front of it, so maybe it will be longer if there will be new interesting results. Depends on the senior panel of NASA. But I hope that we'll be still operating at least 5 years, and we will really have a map like that, and produce new exciting results that the theoreticians will have something, you know, to scratch their head and to get the ideas what's happening in those sources. So this is the, you know, this is what will happen hopefully in 5-6 years. Thank you.
Thank you very much for so comprehensive presentation. And do participants of the seminar have some questions? I would like to congratulate the community of investigation of polarimetry. Indeed, it is very good that such a space mission at last was launched, and we see that there are very nice, interesting discoveries. Of course, most surprising to me personally is this misalignment of rotational axis with the rotation of the disk, how that can be present.
Yeah, so this is really an interesting story, because in Sirius X1, it's not surprising. This is quite young X-ray binary. There was no time for alignment. When you have a supernova explosion, neutron star gets a kick, and so there is no way that it will be aligned, you know, after the explosion. So that's not surprising. More surprising is the older systems which we have, like this one. We don't know the age of that, but you know, this is the probably it's not very young system, yeah. And why there is misalignment here, it's not clear to us. We know that there is Cygnus X2 source which shows no misalignment whatsoever. It has polarization along the jet. There is the jet there measured, so we should we can understand that, because this is something produced at the surface of the neutron star. Polarization can be along the jet, or that's not the problem. But here, why there is a rotation, this is really a mystery. In neutron stars, pulsars, this is not a mystery, right? The pulsar, the X-ray pulsars, young neutron stars, yeah, they are just, and they have magnetic field which is misaligned. They might be themselves aligned with the accretion axis, but even there, not necessarily, because they're quite young systems. But these are presumably quite old systems. So why they are not aligned with the basic accretion moment, like it brings the angular momentum from the accretion, it should be aligned to that. So this is really something we clearly don't understand in this sources.
So we expect new discoveries and see forward for the success in this field of investigations. And thank you very much for your presentation.
Thank you.